Thank you very much for inviting me to talk here and talk about my all-favorite topic, high-dimensional expanders, my current PhD topic. And well, in this talk, I want to explain what high-dimensional expanders are, where they come from, and in the second part, tell you how my colleague Laura and I used Kac-Moody-Steinberg groups to construct high-dimensional expanders. Well, high-dimensional expanders come from a more classical term of expander graphs, which have been around in mathematics for a while now and turned out to be extremely useful both in mathematics and computer science. So it was kind of a natural thing to think of, okay, how could we maybe have generalized this notion? And basically what happens was, instead of just looking at graphs which have vertices and edges, 0 and 1 dimensions, we go to higher dimensions as well. So we include triangles, tetrahedrons, and so on. So we end up with a simplicial complex. I want to say, what does expansion mean there? But let me start with the graph case first. When I talk about expander graphs, you should always have in mind the picture of a good communications network. So imagine your vertices represent parties, and you want them to connect via, I don't know, phones, cables, computers that communicate, whatever. And you want the network to be fast and reliable, but at the same time, it shouldn't be too expensive. You don't want to have too many edges. So that's the kind of the idea. And to formalize it a bit, when we talk about expander graphs, we'll not only talk about one graph, but always about a family of graphs, an infinite family of finite simple graphs, where on one hand, we want the number of vertices in each graph to grow to infinity, so that the graphs get larger and larger and larger, but at the same time, we bound the degree at each vertex uniformly. So locally, we should still not get more and more edges. Locally, it should still be the same number of edges around each vertex. So we want the graphs to be deregular. And then, so that kind of mimics that we don't want to be too expensive. And then for the third part, we want that everything is well connected. And well, the mathematical term to express that is to say that our graphs are epsilon expanders for some uniform constant epsilon. And now I want to explain what being an epsilon expander mean. How do we measure being well connected in a mathematical sense? But for that, we need to develop a few tools. I first have to tell you what the graph Laplacian is. And I will do that in a bit of detail, just so that later on, when we go to higher dimensions, I hope you can see the similarities. So let's start with a finite simple graph. And we look at the L2 of V, so the space of functions from our set of vertices to the real numbers. Or you can just think of vectors where each entry is indexed by a vertex from our graph. On that space, we can define an inner product between two functions, which is just the sum over the products of the two values, and we weigh it by the degree of each vertex. Further, we need to fix an orientation on the edges. So for each edge, we say, okay, this is the initial, one of the vertices is the initial vertex, the other one is the terminal vertex, but we can do that in an arbitrary way. It won't matter in the end. And now we can define an operator delta that maps functions on the vertices to functions on the edges. Well, we're saying if I evaluate a delta f at an edge E, I'll just take the value of f at the terminal vertex minus the value of f at the initial vertex. And now, since we defined an inner product, we can look at the dual of that operator with respect to this inner product. We concatenate it with delta itself, so we get an operator from our functions on vertices back to the functions on vertices. Well, you can also think of this operator just as a positive semi-definite matrix, and there's an easy way to describe what delta is doing. So if we evaluate delta f at a vertex V, we basically get the value of f at that vertex minus the average of f around around the vertex V, so at all the vertices U that are connected to V by an edge. And well, I already said this is that all the eigenvalues are non-negative, and it turns out the smallest eigenvalue of delta will always be 0. And the second smallest eigenvalue is now strictly positive if and only if the graph we started with is connected. And this already hints at that the second smallest eigenvalue is really the one we should look at when we want to know more about the connectivity of the graph. And this will really turn out to be a good notion. We'll say that a graph is an epsilon expander if if the second smallest eigenvalue of its Laplacian is greater or equal to epsilon. And what I wrote here is another way to express this second smallest eigenvalue. And the reason I wrote it is that we'll encounter something similar in the high dimensional case. So we can get this second smallest eigenvalue by taking the infimum over all functions on the vertices that are orthogonal to the constant 1 function. And then we look at this quotient of the inner product of delta f with f and divided by the inner product of f with itself. And by some linear algebra arguments, this will be the second smallest eigenvalue. Again. All right, let's move to higher dimensions. So the object we study now is a simplicial complex. We want it to be finite, so a finite number of vertices. Our complex should be d-dimensional, so the maximal faces should have d+1 vertices. And the simplicial complex should be pure, which means that every face is contained in a maximal dimensional face. Similar to before, where we oriented the edges, we still need to fix somehow in orientation or in order. So we just enumerate our vertices or order them in some arbitrary but fixed way. The last ingredient that we need is an abelian group, a group of coefficients. I already write f here, since later on we'll either plug in the real numbers or the field of 2 elements. All right. Next, I want to fix a few more notations so that we all have the same language to talk about this cohomology. So with x of I will denote the set of I-dimensional faces of x. And the set of I cochains, Ci, is just a set of all functions from the I-dimensional faces to our abelian group F. To define the map delta, similar to what we've seen before, I need to introduce this oriented incidence number, which if I'm given one I-dimensional simplex sigma and another simplex tau of dimension 1 less than sigma, well, one thing that can happen is that tau is, of course, not contained in sigma at all. Then this incidence number, they're not incident, so it should be 0. If tau is contained in sigma, well, then tau is basically sigma, but just we remove one vertex. And depending on the index of the vertex that we removed, this oriented incidence number will either be -1 or 1. It's just a technical tool to implement this orientation. Now we can define our the co-boundary map, which will map I cochains to I+1 cochains. So again, we go up in dimension. And delta A of F evaluated at a simplex sigma will be, well, we sum over all simplices tau f of dimension I, where we can evaluate f at tau. If we multiply with this incidence number, so in particular, we'll only sum over all taus that are actually contained in sigma here. And while you can try to think back, if I is 0, so we're going from 0 to 1-dimensional things, and this is exactly the delta that we had before for the graph case. And just as it's customary in cohomology theory, we'll denote by Zi the kernel of delta I and call the elements cocycles. Bi will be the image of delta I minus 1, and the elements are called coboundaries. And it turns out that every coboundary is a cocycle, so we can look at the quotient of Zi mod Bi, and this will be the ith cohomology group of X. Okay. So far about so much about cohomology of the simplicial complexes. Next, we kind of want to measure the expansion. We want to measure the connectivity. So we need some kind of norm or inner product again. And here I will restrict myself to do two different cases for the coefficients for the abelian group F. So for the first one, first I want to look at coefficients in the real numbers. And in that case, I can again define an inner product, like in the graph case. It's really, we're doing exactly the same thing, where now the degree of a simplex is just the number of maximal dimensional phases that contain the given phase here. And this gives our space of cochains a nice Hilbert space structure. The second case I want to look at is over F2. And in that case, we can only define a norm on our cochains. And this is, we do that by summing over all phases that are in the support of F, so that get mapped to 1 by F. And we weigh this by the degree of the phase, and then normalize by the number of all maximal dimensional phases and this binomial coefficient. Now let's have a look at what we can now do in the case where we look at the real numbers. We had our inner product, so we can again look at the dual of delta as well. And here we have two different options of defining our Laplacian. We can first kind of apply delta I to go from the I cochains to the I plus 1 cochains, and then apply the dual of delta I to go back to the I cochains. That's kind of, we go up in dimension and then down again. Or we could first go down with the dual of delta I minus 1 and then go up. And it turns out if we sum those two operators, we get something that is a reasonable generalization of the Laplacian now to this higher dimensional setting of simplicial complexes. Well, and now to measure the expansion, we want to do something similar to looking at the second smallest eigenvalue. And we'll do that by looking at the infimum overall cochains that are orthogonal to the space of coboundaries. And we, similar to the graph case, look at this quotient of the inner product of delta F with F divided by the inner product of F with itself. And I hope I could convince you that this is really kind of a generalization of what we did for the graphs. And to see how this relates to the next definition, I also wrote this down in terms of the norm induced by the inner product. So it really just depends on the delta I here. And well, now we can call a simplicial complex an epsilon spectral expander if these values lambda I are all greater or equal to epsilon for all suitable dimensions I. I quickly want to mention what happens in the case with F2 coefficients. Well, here we only had the norm, and what we'll do is measure kind of the similar to this quotient here. Now we'll look at the norm of the image of F under delta I and divide by the distance of F to the space of the cocycles. And this will give us the minimum of all those quotients will give us the coboundary expansion constant that if you know more about expander graphs, this will be a generalization of the notion of a Cheeger constant. And we call a simplicial complex an epsilon coboundary expander if, well, this coboundary expansion constant is bounded by epsilon, and if all the cohomology groups are trivial. This is a quite quite strong assumption that really these cohomology groups are trivial. So that's why there was also the notion of co-systolic expander introduced, which kind of is still strong enough to get some results in application, but does not no longer require that the cohomology groups are trivial. And just for technical reasons, we also have this assumption on the size of co-cycles that are not co-boundaries. So much about the definition from the cohomological side. How do we actually work with these things now? And for me, or for us in our work, the definition of a high-dimensional expander that we actually use is this local version, where if we're given a simplicial complex, it's called an epsilon local spectral expander if it's very well connected. So the one skeleton is connected, and for every phase of dimension at most d-2, the one skeleton of the link is connected. That's the first kind of assumption. And the second one is, if we look at those simplices where the links are actually graphs, so the simplices of dimension d-2, and then we look at the graph expansion, they should have a uniform bound of epsilon. And this is something we can really check. Looking whether one skeleton is connected is doable. Looking at the graphs and showing that they're expanders is something people have done for a long time. So that's all kind of something we can handle. And then we can use a very nice theorem from Oppenheim from 2018, where he proved that if we have a local spectral expander where the expansion constant is large enough, then the simplicial complex is actually also a spectral expander in this cohomological Laplacian kind of sense. And I just quickly want to mention, because it's a nice result, there's also a theorem, a similar result about the co-systolic expansion that says, well, if all the links in our simplicial complexes are co-boundary expanders, and the whole thing is a good enough local spectral expander, then the d-1 skeleton of our simplicial complex will be a co-systolic expander. So again, we have somehow a local to global result that makes life a bit easier when you want to show that something is a high-dimensional expander. Now, are there high-dimensional expanders? Well, luckily, I would say the complete simplex is both a spectral and a co-boundary expander. Otherwise, the notion would be a bit strange, maybe. Spherical buildings are also a nice example of both spectral and co-boundary expanders. But that would make our life a bit too easy, because remember from the first slide, actually what we want are infinite families of bounded degree high-dimensional expanders. So we want infinite families of simplicial complexes now, such that, well, each of them is an expander with a uniform constant in whichever term we choose to look at. We want that the degree of every vertex in every complex is bounded by a uniform constant. And of course, the number of vertices should grow to infinity. And I think I haven't mentioned it yet, so I'll do it now. In the graph case, it didn't matter whether we look at the Laplacian eigenvalues of the Laplacian or at the Cheeger constant or other definitions. For infinite families, all these notions are equivalent. But in the higher dimensional case, there are really counterexamples to show that these three terms of expansions are not equivalent. So yeah, we have to do more work in this higher dimensional case. But there are examples of high dimensional expanders. The first construction was due to Lubotsky, Summers, and Vishnu in 2005, where they used quotients of Brouhatit buildings by co-compact lattices to construct both infinite families of local spectral and co-systolic high-dimensional expanders. In 2018, Kaufman and Oppenheim gave a new construction that used what is called a coset complex over SLN to get local spectral expanders that are a bit more, I don't know, easy to grasp than quotients of buildings, I would say. And this construction was generalized by O'Donnell and Pratt to coset complexes for arbitrary Chevrolet groups. And now our work can again be seen as a generalization of their results, where we now consider finite quotients of so-called Kac-Moody-Steinberg groups. And this will also give rise to local spectral expanders. And that's what the second part of my talk should be about, explaining what these coset complexes are and which groups we take for our construction. Right, so for coset complex, we need two ingredients. We need a finite group, and we need a family of subgroups of our group G. And then the coset complex will be a simplicial complex where the vertices are the disjoint union of the cosets. And well, the maximal faces should be of the form we have one coset from each subgroup, and we shift them all by the same G in our group G. And then we take the downward closure to make it a simplicial complex. In particular, you could say that two vertices are adjacent if and only if their indices are different and their intersection sets are non-empty. And coset complexes maybe not under this name, but they appear a lot whenever you have a group acting on a simplicial complex. Because of course here G acts on the coset complex by left multiplication, and the HA will be the vertex stabilizers and so on. So you have a nice structure. And for example, buildings coming from Bn pairs can be seen as coset complexes, even though not many people write it down in that way. But so I think that's a very useful construction. Now, which groups do we plug into this construction tool? Well, we start by fixing a finite field of size at least 4 and characteristic different from 2. We look at SL3 over the polynomial ring in one variable over that field. And we consider these 3 subgroups that, well, they don't come out of nowhere. They come from our Kac-Moody-Steinberg groups in the end, but yes, and now we want an infinite family of complexes, and we do that by choosing an infinite family of irreducible polynomials, such that their degree grows to infinity. And then we look at the entry-wise projections, where we go from the polynomial ring to the polynomial ring, modded out by the ideals generated by these polynomials Fm. And well, then we look at the images of the subgroups under this projection, and we do our coset complex construction and get an infinite family of bounded degree spectral expanders. So now that we've seen this example, I want to give you a brief idea of where they come from. I try to explain what Kac-Moody-Steinberg groups are, but so it all starts with a Dynkin diagram. If you don't know, the Dynkin diagram is, think of a finite graph where you can either have 0, 1, or double edges with an arrow. And for each vertex in the graph, we'll take one copy of the additive group of our field. And for all pairs of vertices, we want to define a group where these ui and uj embed into. And we'll distinguish 3 cases. So if the vertices are not connected, this will be just a direct product. If the vertices are connected by a single edge, we'll take the Heisenberg group. And if the vertices are connected by double edges with an arrow, we take this specific subgroup inside SP4. And well, the way they look, the subgroups themselves come from Kac-Moody theory now. And to get the Kac-Moody-Steinberg group, we take the direct limit of these ui and uij with respect to the inclusions of the ui's into the uij. So we get the group generated by ui and by the groups ui and uij, and we have as relations we identify an element of UI with its image in UIJ. And if the Dinkin diagram that we started with is not spherical, then the K-mass group will be infinite and the UIJ embed into it. So it does not collapse, which is very nice. Well, for each subset of vertices of our Dinkin diagram, we can define a subgroup UJ that is just generated by all the kind of groups corresponding to the vertices. And if the subdiagram induced by this subset of vertices is spherical, also the group UJ will be finite. It's also known that the KMS group is residually finite in many cases. So we have a lot of finite quotients, which is nice. And in particular, if we start with an affine diagram, the KMS groups has a quotient inside Chevalier groups over a polynomial ring. So in particular, for example, over SL3, which is kind of where the example comes from. And now we can come to our main theorem, which says that if we start with a KMS group, well, with a finite field of size at least 4, we want a Dinkin diagram such that whenever we remove one vertex, we should end up with something spherical. And so that's the first ingredient, our KMS group. And the second ingredient is we need a finite group. And that is a finite quotient of our KMS group, such that the quotient map needs to be injective for all these subgroups UJ. And we need even more injectivity. We need that the intersection of the images of two such subgroups is the image of the intersections. And if we have all those conditions, and we look at the coset complex of our finite group G with respect to the images of the UI, where we always remove one of the indices. So these are the subdiagrams are just as large as possible, but still spherical. We look at this coset complex, it will be a local spectral expander where the expansion constant is independent of the finite group G and the quotient map phi. So in particular, if we have an infinite family of finite quotients that satisfy these conditions, then we get an infinite family of local spectral expanders. And of course, now the next question, which is ongoing work, is are these complexes also coboundary or co-systolic expanders? And so far, I'm quite positive that we'll indeed get that the links are coboundary expanders, and the full complexes or their D-1 skeleton should be a co-systolic expander, but that's, as I said, still a work in progress. And I want to end my talk in the last minute with a question for you, because I realized during the last conference I've been to that this coboundary expansion constant, so the idea of measuring the size of an image of a cochain and comparing it with the size, with its kind of distance to the coboundaries, also appeared for other cochain complexes. So I was wondering if anyone who works with cochain complexes or chain complexes in a different setting also looks at these kind of numbers. And concretely, what I saw was someone talking about bounded group cohomology, and then this, or the inverse of what was the coboundary expansion constant for me was for them the vanishing modulus. So that would be very interesting to see for me if anyone else has seen something like that. All right, thank you.
Let's thank Inga for her talk. Are there any questions for the speaker? Any questions? Okay. Okay, maybe I'll ask one. So your main theorem on the previous slide, is there any idea about whether this theorem would hold with fewer requirements or?
Sorry, what? How?
I'm sorry, maybe I'm not loud enough. Is it possible that this theorem could also hold with fewer restrictions on the KMS group, or is everything here just strictly required? Like, I'm not sure if what I'm asking makes sense.
Well, so
Is it an if and
everything
only if
here is necessary, but you don't. So I think, or an idea of myself is that you don't need to start with a KMS group here. You could have something, a direct limit of certain local groups that that would still work. Like, it's just that KMS groups have a lot of very nice properties, and a lot of the properties are necessary, but like you could have a direct limit here with some other subgroups Uij that still have a nice kind of local behavior. You need, so a nice thing why I chose these specific choices is basically if you take the coset complex over Uij with respect to Ui and Uj, it's known that these are expander graphs and with nice constants. I think that's basically where this choice, or why this choice works very nicely here. But in theory, you could try to find other groups as well. So, yeah.
Okay, thank you. Were there any other questions? I just wait 1 minute. Okay.
Yeah,
Yep.
oh, sorry. You had, like in the definition of the expanders, you had this, in these parameters, this like you were bounding below this expansion constant and bounding above the degree. Do you have, like, can you do it for, does this construction work for all settings of those parameters, or do you have like bounds, like if your degree is lower than this, for example? And next question, I guess, could you do it for, is there a question of pushing those bounds wider?
I think you can get away basically with any expansion constant, but like there is a dependence between the degree and the expansion constant. Like both depend on the size of the field, I would say. Yeah. So you could get better and better expansion by increasing the size of the field, but you would also increase the degree. Yeah, I'm not sure if there's a way around it, because I guess you would really have to find different like Uijs basically to start with to get a better expansion, independently of the degree. But of course, I mean, if you have a larger degree, your expansion will be better. So it's kind of a behavior that is to be expected. Yep.
I see. Thank you. Yeah.
Okay. Are there any further questions? Okay, let's thank the speaker one more time.